All right, so let's recap what we have. So we have this f in the entire application now, and this makes the entire application completely open for extension, right? Just the interpreter needs to say what it needs, and the main is forced to provide it. And by the way, this also means that your interpreter should be as specific as possible. So for example, we could go to the evaluate over here, right? And we can say, we need the entire monad. This thing is going to compile, right? Because the monad is sort of like bigger, right? But the main still needs to provide it. In this case, it was easy to provide a monad for ID, but the point is that it's not always so easy. In fact, so if you look at this expression, and this is what I meant in the previous video, that in this video it's going to be super clear that we actually need to divide this thing. So if you look over here, as I showed you in the beginning, this thing needs just a functor. This thing needs just an applicative. Well, not just the applicative. The applicative is the biggest thing over here. Okay, this one needs just a functor. This one needs just apply, and only this one needs the applicative. So what we're going to do now is we're going to go and we're going to split our expressions into multiple ones. It's going to be real quick. So I'm going to paste it 2 times. So this one is going to be literal, and we're going to remove these guys. This one is going to be negation, and it's going to be this. And this one is going to be addition, and it's going to be that. All right, so now everything everywhere is not going to compile, obviously. So we're going to do the same thing over here. So we're going to copy that, have it 3 times in total. Okay, so the first one is going to be called literal. Okay, and it actually needs apply. It's going to be literal over here. Okay, so it's going to be this, it's going to be that. All right, so this guy, the next one is going to be so this is going to be negation, and negation only needs map, right? So it only needs a functor. So we're going to have a functor over here, throw out this one, throw out this one. Okay, this one is addition, and same thing over here, addition over here, and addition needs only apply, right? Apply. Okay, so look at all of these guys. They're now, they're now all the same, sort of, right? So we have like these DSLs for the multiple ones. Now addition looks exactly like the multiplication. It's just like this is the only difference, right? And you could abstract it even more, with like monoids and stuff, abstract away from the integers. Right, so let's go and finish this thing. Let's go to the view, do the same thing. Again, we're just copy pasting a bunch of things. So I'm gonna copy that, paste it here again. Same thing over here. So this is going to be just the literal. So we're gonna do that. This one is going to be negation, and it needs just a functor. All right, so I'm gonna have negation. This one is going to be addition, and it only needs apply. Okay, so we can remove these guys like that. That should all be fine. Cool, let's go into our programs. Let's save that. So now it's basically going to say that it doesn't know expressions. Okay, so everywhere we're going to say expression, we're going to use, okay, maybe not everywhere. Okay, let's like this maybe. Okay, we're going to do literal, and everywhere we're going to do like these expressions, we're going to say literal. Okay, and now we need to be more specific over here as well. So we're going to say that we need also the addition. Let's do them sort of like in the same order as we did. So we also need the negation, which is the negation of f and a, and we need the addition, which is the addition for f and a. There should be a colon, and we need to import them. So this is going to be negation, and this is going to be addition, like this. So at least this one should compile now. Let me maybe copy the parameter list. It doesn't like literal. Okay, so over here we're running into issues with naming. Okay, so by the way, this is a thing that I forgot to mention. Like it's very typical to call these guys like the capital letters of the name of the DSL. Okay, so now we can just do like that. Okay, so yeah, maybe let's do this for others as well. LNA, yeah, why not? LNA. Okay, like this. I usually don't like this one because first of all, like very often like the letter F is used, and then it sort of like collides over here. I mean it compiles, but it's weird visually. And also like, what if you have another DSL that has like that also starts with an N, then you're gonna start having like N1 and N2. Okay, so like usually you would try to use like the context bounds. Okay, but yeah, in this case it's not super possible. All right, so let me copy the list over here. Okay, so for this one we're actually going to need multiplication as well. So let me paste it over here. Let's do that. Multiplication is just going to be an M. Okay, so we're importing L. Oh, notice this one. So this is like one of the benefits that we get now. So in this case, we're only using the multiplication and we're only using the literals. So we can actually throw out all of these, right? So literals and the multiplication, and that should be enough. Okay. Oh no, it's not enough because like this guy, the original expression actually wants negation and addition as well. All right, so I talked too fast. Negation addition. Okay, so we can import L, we can import M, but at least we don't need to import the other ones. Right, let me copy the parameter list. Okay, so this guy, oh, this guy should be actually fine if I just do that. And we import L, N, A, and M. Actually, I'm not super sure about this, but I think if I do this, and if I replace imports with commas, commas, it might work. Yeah, it works. I usually don't do this, but in this particular case, let's make an exception. Let's have a comma over here, and let's have join lines, commas. Yeah, I think in this case it's actually better. All right, so let's go over here. So it has the L, it has the M. But it also needs the others, which is the division, which is going to be D. Okay, it actually doesn't need the M like this, but it still needs the addition, and let me just do that. So it's here. All right, forgot the comma. All right, and the last one is going to need these guys as well. Oh, actually, I forgot this one. This one, come over here. Let's put it over here. All right. Oh, and this one actually needs all of them. So it's going to be L, N, M. No, it's A, M, and D, D, and join the lines. Whoa, that's a lot of sunlight. All right. Comma like this. And another cloud. All right. So this thing finally compiles. So now we need to go to main, and basically everywhere where we say dot expression dot DSL over here, I'm going to say dot literal dot DSL, and I'm gonna press Control Enter. All right, finally, cool. So this is how the whole thing looks like. So this program needs like all of the three. This one needs all of the three. Multiplication needs more. This one needs. This is the view. Actually, this one, multiplication in the middle. Okay, it uses all of them. But this one, okay, it uses the other one. Okay, so, but still, like this is basically now like super divided. And by the way, this is where you see like that this was better to specify the type over here instead of everywhere over here. All right, so again, let's recap. In the beginning, we started without any arrows. So like sort of like this, we didn't even know about ID, but like now that we do, if we trace it back, we kind of knew that our initial design was ID. Then we realized that we needed arrows, so we added option. Then we realized that options were not enough. Now we had an other, so that we can have like two different arrows. And by the way, we're not even actually showing arrows. Let's actually have a program that actually has arrows. In fact, I don't want to waste your time, so I'm actually going to copy paste it. So if we go to program, and I'm going to do that, and I'm going to have one of these. Okay, so this one is called division with two errors. And okay, so as you can see in my script, I did that. Okay, so it needs the literals, the addition, and the division. Okay, so we're going to do L, A, D. We're going to do that trick again. We're going to use commas.
Okay. So basically what we're doing over here, we're adding two divisions, and this first one is going to throw an error, right? The one that, the division by 0, and this one is going to say that this is a division with rest. All right. So if we go to our main, okay, and we're going to copy, let's copy like the last two. Okay, so these guys like this, paste them over here. All right, so we're going to say that this is going to be the division with two errors, division with two errors. We're using too many things. Okay, so over here I just said that we need literal addition and division. Okay, literal addition and division. Okay, same here, literal addition and division. Oh, I removed the wrong one. Addition. All right. It's kind of cool to have a strong type system. All right. So as you can see over here, we have left division by 0, but we're not seeing the other error. Why are we not seeing the other error? Right. So they're not like nested or anything. Right. They're side by side. So we should see that this is an error and this is an error. Okay. And I'm going to show you that now that we have this like final, like no pun intended, but like now that we have this like bulletproof design, how easy it's going to be to see both of the errors. And by the way, let me actually add one tiny thing over here before we tap it into print line. And by the way, notice again, like for the view, ID was enough. Ooh, again, a lot of sun. I hope that my camera is not going to overheat. Okay, so before we're going to print it out, let's actually pipe it into console.read plus result plus console.reset, just so that the arrow is red. Okay, over here. Cool. So we're going to go and we're going to either write a new interpreter, or we're just gonna improve this one. Okay, so we're gonna go and we're gonna find addition. Okay, and we're gonna see what is happening over here, right? So it's doing A1, A2, map M. Okay, so if you've seen my video about error handling, then you know about this thing called par map M. So what's happening over here that we're specifying that we're gonna work with an either, right? Which is, by the way, nowhere near visible over here, right? So only in the division we're saying that we need a monad arrow. Over here we don't see it, okay? But the point is that we're going to say that over here we're not going to use map m, we're going to use par map m. Par map m. And this is also the reason why I told you to use the syntax, because in this case it's going to say, hey, in order to call par map m, I actually need not empty parallel. And without knowing what not empty parallel is, without understanding it, we're just going to go and slap it on here. Not empty parallel, and now this thing is going to compile, and now we're going to see both of the errors over here. It says division by 0, and division ended up having a rest. Right now, because our error thing was a string, it just like smashed all of these strings together. And if you've seen my video about error handling, then you know that if you put this into something like a list, it's going to work out. Before we do that, let's actually go and put this everywhere. Okay, so we're going to say not empty parallel over here, like this. Well, actually, not this one. This one does not need it. So we have negation, we have the literals. So it's basically only like where we have like two things, okay, which is going to be over here, so that we can do par map n. And over here as well, why not? Let's have it over here. And for this, we're going to need to use par tupled. I'm not sure if we need this in the views, but why not? So this should always be like the default, right? So if you see that there are no dependencies between A1 and this is like classic form validation, right? Imagine that we wrote like front end for this thing, for this calculator, right? And somebody would put A1 and A2 in. There's no dependency between them. It doesn't matter which one they put first, right? As soon as at the point where the code is going to be here, it's just going to need both values. It doesn't care which one was calculated first or whatever. All right, so we're going to do this, and we're going to do par map n. And we're going to do it over here as well, par map n, and here as well, par map n. All right. So now all we need to do is we need to use something better for our errors. And again, notice that we're not changing the DSL and we're not changing the programs. We're not doing anything in the programs. It's just the interpreters. The interpreters, they have all the power. Okay. So we're going to go over here. We're going to say, we're not going to use string. We're going to use something like a list. We're going to use a non-empty chain. Okay, of string. Okay. And over here for this, we need to import
Cats data, and that's not going to compile at the bottom. It's going to say, hey, well, you're giving us a string, but you said that you want to give us a non-empty chain. Okay, well, let's just wrap this string into a non-empty chain. Okay, and let's do the same thing over here. I hate it when I bubble lines. VS Code like fucks up all of the indentation over here. Okay, so we just did this, and now in our main, we just need to say that we're not using a string over here. We're using a non-empty chain of strings, and there is an alias for this, which is called either neck. Okay, so we just need to import cats data. Okay, and now that thing is going to compile, but the others are not going to compile, like this one, other neck, and the other one is over here, other neck. Okay, and ta-da! Our errors are accumulated and they're in a list, and it's all good. And we did not need to change the expression. We did not need to change our programs. We did not need to have some weird map and flat map over here. It's only in the interpreters. All the power is now in the interpreters. So because the change is only in the interpreters and in the main, right? Like you're probably noticing this pattern, right? Which as soon as we're changing something in the interpreter or we're adding a new interpreter, in the main, we also need to do the change, and we also need to add something like this. I'm not 100% sure about this, but in the paper there was you know, one of the tagless final papers by Oleg Kisilov are called like finally tagless, partially evaluated, or finally tagless and, you know, partially evaluated staged interpreters. And I believe that because you're doing it like stage by stage, right? So this is one of the stages where you, like, you know, partially evaluate stuff over here, but in the main you need to go in there and actually, you know, finish specifying what you need. All right, now let me make sure that everything is clean. Right, so let me remove the red color actually. All right, cool. So I believe that this is enough. So let's do gcam video4 like this. Let's push it. Let's go and see what's up over here. I think it didn't finish pushing it. Hold up, like this. Reload. All right, so commits. It's 5 of them. Video4. All right, so we split it up everything. We changed option to an F. Everything is split up over here. We're specifying only the things that we need. Yeah, by the way, this is one of the things, you know, like we did like everything gradually, everything like step by step. But if you're being thrown into a code base and you're kind of new to Scala, you're kind of new to functional programming, this is a beast, right? Super hard to understand. Well, not super hard to understand, but there's like so much machinery in here. But that's like sort of the whole point. This whole machinery and everything is in the interpreter. The programs don't really change. Okay, but still, I sort of admit this is kind of hard to understand, but we did it like step by step, and yeah, it should be fine. Let's go and finish scrolling down. So it looks all right. The programs are parameterized with an F now. By the way, you don't always have this thing that you have like an F and an A, right? So if you're doing something like, you know, FS2 streams, then you're gonna have the same. But for like regular business applications, usually you're just gonna have like the F. Okay. So the difference over here is that in our expressions, we ended up like using them over here. Right, so we actually need to know the A, but like the regular application like this one, so if you're going to go to the boundary, okay, we're just going to have the F over here, right? And why? Because like all of these guys, they return a different type, right? So this is going to be an F of to do existing. This is going to be an F of you know, vector to do existing, okay? So we don't need to have the same A everywhere. All right, let me revert this guy like this. All right, what else? Weird imports. Programs, like this is like so beautiful, right? So this original program, again, if we go over here, the original program from the very first videos, it stayed exactly the same. It did not remain, like we did not change anything over here. We just changed a bunch of types around it, like a lot of machinery around it, but the program itself did not need to be changed. I think this is super, super beautiful. Right, let's go and see the main. Yeah, so all of these, like, because we did like so specific, you know, we're passing in like all of these, but all of them are passed implicitly anyway. Sometimes. Looks fine. Like this is like the mains. All right, cool. So what have we learned in this first part of this gigantic series? The first thing is that there was zero hype about effect tracking. We were just trying to solve the expression problem, and effect tracking appeared out of nowhere. By the way, let me show you something, and I'm not going to commit this. I'm just like showing you a couple of things. Okay, so
let me do that real quick, like this and like that. Let me comment this out. Let me rewrite this real quick to this other syntax. Okay, we're going to have implicit, and we're going to have the M, which is going to be the mono error, and we're going to have the F, and we're going to have the non-empty chain for string, and we're also going to have N, which is going to be non-empty parallel for this F. Okay, so it still compiles if I'm not wrong. So this is going to be division of F and int. Okay, so this is just a different syntax. Okay, however, if you were to hard code this to an other, okay, so this is going to be type f of a, right, and we're going to make sure that it doesn't come in over here, right, like this. So now it can be a val, right, because we're going to use like this f over here everywhere. Okay, oh, it still needs to be a def because we need like these guys. Okay, f of a, and this is going to be an other non-empty chain of string or an a, right, like this. Okay, or even either neck. Okay, like this, a little bit shorter. Okay, so what I'm showing you basically is that even without tagless final, you can still sort of have like effect tracking. Okay, so over here now you can actually go and start using like right and left, because now like the f is hard coded to an other. So technically this is not exactly effect tracking, so it's not like so bulletproof, but then again, like the initial effect tracking was not bulletproof to begin with. I'm just saying that like there's nothing like super I don't know, magical about like this f. It's just that it gives you this ability to specify somewhere else, and because things over here are not going to compile anymore because it's going to say, hey, I don't have flat map, I don't have map, you end up specifying the things that you need. So it's kind of like a little bit more enforced. Like effect tracking is a little bit more enforced in tagless final. But again, the whole point of tagless final is not effect tracking. All right, let me revert this whole thing. Come on, click, revert. All right, cool. Number two, all of our issues were solved once we first of all, raised everything into high kinds, and we abstracted them away, right? So we had like this f, and I told you that I would explain you why we use the letter f and not some other letter. In fact, we use multiple letters. Like sometimes we have an f of a, and then we go like g, G like this and so on. We just keep going like we're starting with F, but we're always using F. And one of the reasons we use F is because like at least in the Scala community, it stands for effect. So you can put it like any effect type you want, like, an either or a cats effect IO or ZO or whatever. But another view on this is category theory. And this is actually very, very important. And I'm not an expert in category theory, but I'm pretty sure that the reason why we use the letter F is because it stands for half of a functor, right? So it has something to do with a functor. Now, what the hell is half of a functor? Now, in category theory, a functor is a thing that does two things. The first thing that is, very popular and everybody kind of knows this, it maps the morphisms from one category to another, right? So morphisms in programming, they're just functions. So basically, it means that you have a function that goes from an int to a boolean, then it can lift it into something like options, right? And now you have a function that goes from an option of int to an option of boolean, or it can lift it to lists, right? Now you have a function that goes from lists of ints to a list of boolean. Okay, so this is one of the things that a functor is doing. But there's another thing that the functor is doing. The functor is mapping. Well, I'm not going to use the word mapping. The functor is moving also the objects, the categorical objects from one category to another. What does this mean? It means that if you give it an int, it's going to give you an option of int. If you give it an int, it can give you a list of int, right? And so on, or an either and whatever, right? So there are like these two things, okay? So it can move the functions over, the morphism over, and it can move the categorical objects over. And the categorical objects are types, at least in the categories that we programmers care about, right? The closed Cartesian, Cartesian closed categories. By the way, it's super important to understand that the objects in category theory, they're not values of the types, they're types themselves, right? So every object is a type. So when I'm saying that a functor moves objects over, I'm not talking about values. Right? In order to move the values, you would need something more than a functor. You would need the applicative, right? So if you want to raise a 5 into an option of 5, you would need an applicative. But you don't need an applicative if all you want is to
move the entire type int into the type option int. So now if we go to evaluate, and if we look at something like over here, we're going to see that this is a full functor, right? It's going to move the objects, right, from this underscore to f of underscore, and it's going to move the methods, right? So we have the map. However, over here, it's only half of a functor, right? It knows how to raise some type A or some other type into an f, but it doesn't know how to move the functions, right? And this is why this is called a half of a functor or effect, you know. But at least it doesn't have anything to do with final. Okay. By the way, notice that in this entire series, we didn't really use like, you know, the typical effects, you know, the effects that can suspend or delay computations, you know, effects like I/O. I'm actually going to show it to you real quick. So in our entire application, we actually don't need to suspend anything, but we could, right? So remember how we had like these like very simple programs over here. Right, so there's a very simple one. So remember how in the beginning, you know, we were able to put something else over here like an option, right? And it would have just worked. Like, so right now we're kind of like over specifying a couple of things. So it says, you know, I can't find like a non-empty parallel and stuff. So we could try like to put like another neck in there and stuff, like other neck of you know, star. No, this is going to be a string and this is going to be a star. Let's see if it's going to work like this for this guy. Yeah, it does, right? So we can like specify the things that it actually doesn't need. By the way, notice that it's not actually going to work for the regular either, I believe. Okay, it's going to work for a string, but it's not going to work for nothing. Right? Yeah, it's not going to work for nothing. That's what I thought. Okay, but the point is that we can always like wrap these things into like more things if we don't need to, right? It's kind of weird sentence, but this is actually how I meant it, right? If we don't need to, we actually can do that. All right, so let's go and do like ID over here. Okay, so what I'm going to show you is how we could, you know, wrap this again like into IO, even though we don't need to. And this is going like a little bit too close to the MTL style of programming, but still. Okay, so let's go to you know, just for fun, build, and we're gonna go over here. So this is the interpreters. We're not gonna need. Are we gonna need them in the interpreters? No, probably not. So we probably need this only in the main over here. Okay, so I'm gonna copy that. Okay, and I'm gonna use Cats effect. Cats effect, latest version I believe is 2.13. All right, let's allow SBT to finish real quick, and let's import the changes. Come on, import the changes. All right, so if you go to main, if I go and I copy like these two guys. Okay, put them over here. Let's switch back to the terminal. All right, so first of all, let me rewrite them real quick like this one. Let me rewrite this to other non-empty chain of string, because it's going to be like a little bit easier to understand like this. Okay, so what I'm going to do is I'm going to duplicate this line. I'm going to do that. Okay, and I'm going to wrap this entire thing. So I'm going to interpret, you know, again, remember this like partially evaluated like stage interpreters. So I'm going to ask the interpreter to have an either t over here, right? So this is going like into mono transformers and stuff. Okay, so I'm going to have a rectangular brace over here and over here. And now we need to say like which effect we want. So for example, we could use ID. Okay, so we might need an import. Division, what does it say? Wrong number of type arguments, which means I did something wrong with the brackets over here, probably like this. No, oh yeah, I don't need the other anymore. I just have the non-empty chain like this, like that. Yeah, okay, so this is exactly why I commented out this thing, so that I can show you like basically that all of these things are still there, right? So it's basically like this, right? So but now it's like wrapped into an other t, which is why like over here we're seeing that this is like an you know, like an other t. Okay, so what we can do over here, we're going to do like tap print line, but we can also do tap, and we're going to say, okay, let's, you know, unwrap this whole thing from either t, and let's pipe it into print line. Okay, so with this like construction, right? So you see like we have like a lot of layers. Okay, chain of left of either t, and over here when we're saying like dot value, then we have, you know, we got rid of either t, right? So we constructed this thing and we deconstructed it again. Okay, and now if we were to add like another layer, if we were to say, you know, let's use the Cats effect IO over here, right, then we would be able to also go over here, right? Notice that it says like this is an either t of function 1 because of the way IO is implemented. But now we can go over here to value and we can also do unsafe run. Okay, so I hope that this is like not not too confusing, and for this we might need it's called unsafe run sync. Unsafe run sync. Okay, like this. All right. I hope that this is not too confusing, right? But this is like something that we're gonna do. Like this is something like that is like a little bit more typical, right? Usually you have this is like a typical sort of stack, right? You have some sort of IO, you have some sort of error handling. You wanna like throw errors together. This is a sort of like the minimal stack in the regular business applications. All right. Let me throw this one out. Again, I'm not gonna commit this because this is getting like too far into the MTL style of programming. MTL stands for monotransformer library. We're probably gonna talk about this some other time. I actually don't really want to make a video about monotransformers because monotransformers are usually frowned upon because they're kind of slow. Like this thing looks kind of small because we did this change like only over here, but this stack is now being inserted in your entire program, right? So every time you say pure, you're wrapping this thing into what are we having here? Into an either, and then into IO, and then into an either T, I believe. Right, either T of IO and then of an either, yeah. So this is like a gigantic stack and it's actually kind of slow. So usually what you would do is like you would not use monotransformers even here. You would implement this effect, all right? So all you need to inject over here, right, into this DSL is an F that has, hold on, this is not what I wanted to have. So the strongest thing is this one, right? So you need to put in a type that has like all of these things. Okay, and you can manually implement it, and this is how you usually optimize. And this is like one of the beauties of Tagless Final is that you have to do this optimization only in one spot, only over here. Okay, but this is too much. Like this was supposed to be like a beginner introduction to Tagless Final, but now we're going like too crazy over here. And by the way, one more thing about category theory, like this is not a coincidence that we're using functors, and this is also not a coincidence why all the so-called DSL hierarchies, why they're called functor hierarchies, right? Cats is not the only one. There's, for example, Izumi, which has bifunctors and trifunctors and stuff. There's Cats Effect, the entire Cats ecosystem. There's the Scala Z ecosystem, right? So you can write your own, right? You can have your own DSL, but all of them somehow, for some reason, they all start with functors, and the reason for that is that functors have this awesome property that they preserve structure. Now in category theory, this means that that you preserve like all of the morphisms, like none of the morphisms go away, like none of them disappear, and also they point like to exactly the same objects. Some of the objects might disappear, right? Some of the objects might collapse, but all of the morphisms are going to be there and they're going to behave exactly the same. And by the way, this is a typical categorical view that the morphisms are way more important than the objects themselves. And by the way, this brings me back okay, let me finish this story first. So it preserves structure, which is exactly what gave us the ability to, like if we had this design from the very beginning, it gave us the ability to easily go from ID to option to either NAC, and now to either T with ID and either T of the Cats Effect IO. And through all of this, the structure of our programs was preserved. I don't necessarily mean that the syntax didn't change, right? Because we had to add like types and stuff, but like the behavior, right? The morphisms, something made sure that all of these errors they still behave the same. Now they're wrapped into a bunch of things, but they all kind of behave the same. Okay, and this is the thing that you get from functors. This preservance. Anyway, the structure of the morphisms is preserved. Let's unwind a little bit. Just a second ago, I said that in category theory, the morphisms are more important. The biggest advice I can give you, if you're working somewhere, you probably have way bigger problems than rewriting the whole application to the Tagless Final style. However, there's a chance that you're dealing with options everywhere. You're dealing with others everywhere. You're dealing like with lists and all of that stuff. Do not pattern match on them, because if you start pattern matching on them, it basically means that you care about the objects more than you care about the morphisms. As long as you keep using just map and flat map and all of these things, it's going to be much easier to switch an option to an either, right? Because they all have like this very similar structure. Okay, so pattern matching considered evil. One other thing that I want to mention is that, abstraction, clearly in this case, it gave us value, right? But it always comes at a cost. First of all, educational cost. But secondly, also is that we technically have way more code now, Okay, and we could abstract it even further. For example, why is this hard coded to an integer? Or over here, our interpreters, why are they all only for integers? If just for fun, if we were to copy like all of that, right? And I'm gonna do like evaluate 2 over here, right? I go everywhere over here, right? And I'm gonna do I believe that this is enough. Okay, I'm gonna do like doubles over here, for example, right? Everything kind of compiles still, right? Except for this one, right? Because this one, it starts with an integer, so we need to do like 2 double over here. Okay, but everything else, kind of compiles. Yeah, this needs to be integer. Okay. Right. So everything else kind of compiles, right? But now you're gonna go down over here and you're gonna see that this division is never gonna fail, right? So remember, like for doubles, like these things are not gonna, they're not gonna fail. So you're gonna realize that the interpreter for doubles, it actually doesn't need any of these things. However, if you were to abstract away from this integer and double, right? So if we were to go over here and we would say that this is going to be, there's going to be some type A over here, right? And we're going to have like A over here and so on and so on, right? So for example, like this thing is still going to compile. Probably, no? It takes no time expected 1. I'm sorry, this still needs to be an F. Okay, so this one, for example, is still going to compile, right? Obviously, we're gonna have like issues somewhere else. What does it want? Okay, maybe this is a bad example. Okay, so I'm not going to show this to you, right? But basically, we could get rid of this integer somehow, and we could have like an abstract type over here, and then once we would arrive like somewhere over here, we would need to say, okay, well, it can be like any type, but this type needs a semigroup over here, right? And so on and so on. So we could have like kept pushing this thing and kept like abstracting away, but the point is that abstraction is awesome, but it comes at a cost. So you don't always need to abstract like to the max, which brings me basically to the last point. Tagless final can be super scary, but only if you push it like to this maximum, right? So remember, like in the beginning, well, not in the beginning, but like just in the previous video over here where we have the interpreters, which is hard coded the type, which is like a lot of teams are doing this. They're not going like this full effect tracking route. They just go and say, we're gonna have an option. And one day we're going to need to switch to another, whatever, search and replace. Not such a big deal. Also, don't worry too much about like splitting DSLs. Like actually, usually you would start with like very, very small DSLs and then you would bring them together. So we kind of did it like backwards and stuff, but like don't worry too much about it. All right, I also wanted to show you how it looks like in Scala 3 because there are a lot of improvements for implicits in Scala 3, and I actually might insert a tiny video before we're going to start rewriting the to-do app, but maybe I won't. Maybe I'll do it in the end, or maybe I'm not going to do it at all. I'm going to wait until Scala 3 actually comes out. So yeah, maybe in the next video we're going to start rewriting the to-do app. For now, I hope you enjoyed this part of the series so far. And for now, as always, it's been Vlad, devinsideyou.com. Don't forget to like this video if you did, subscribe if you want to improve the developer inside you, and if you learned something today, consider supporting me on Patreon and thus watch my videos weeks and sometimes even months before everyone else. And most importantly, take care.